Okay, as we get started today, just a couple of reminders about this week. So the the CASA sign up should have already started yesterday. I think if you missed signing up yesterday, you're probably going to be stuck with leftover times. So make sure you deal with that. Uh, so the first exam is 2 weeks from now. So make sure you're ready for that as from a sign up standpoint. And then um, Thursday of this week, I'll be away for a business trip. I sent an email about this if you didn't see it. So on Thursday we'll have class. It'll be led by Professor Larson, and I think his plan is mostly to just review recent material or answer questions on anything recent. So come prepared for that. I have a recording and lecture notes posted for what we would have normally covered, so that'll be sort of on your own. But Professor Larson will be here to answer any questions you have, so it's still good to come on Thursday. I certainly recommend that. All right, so let's jump into then what we're doing today. We're going to finish chapter 2 today and then launch into chapter 3, which will be the last chapter that's covered on that first exam. So what we're going to start with today are we talked about last time electron configurations and the idea that we can use the periodic table to predict them. And so because elements are arranged on the periodic table according to their valence electron configurations, that means that their relative locations in the periodic table also allow us to predict some of the key properties. So the last topic in chapter 2 that we're going to start with today is going to be a few things where we have certain properties of elements, certain properties of atoms themselves that we can use the periodic table to predict relative trends in those properties, that, which one is higher or lower between different elements. So the first one we're going to start with is called atomic radius. Now, atomic radius is a little bit of a weird concept for us to think about at first because we just got done talking about the idea that the electrons in the atom are sort of form a wave function. There's sort of a probability of finding them in a certain place, but we can't say exactly how big an atom is. We don't know exactly where the electrons end or where there's not really a defined region. So the way that we sort of think about atomic radius is that when two atoms bond together, which is going to be the big chapter 3 topic that we're getting into soon, when two or more atoms bond together, the distance between the nuclei of those atoms is classified as the radius. So if you have a metal, for example, what we'll learn very later on in the course in like chapter 9, way down the road, is that metal atoms arrange themselves into these sort of regular 3-dimensional arrays. And so if we have the nucleus at the center of each of those atoms, indicated by the little dot there, we can measure the distance between the nuclei. And that radius, which is sometimes called the metallic radius, but more generically the atomic radius, would be 1/2 of that distance. And so we're sort of saying that when two atoms get as close together as they possibly can in a metallic structure, for example, there's going to be a nucleus here, a nucleus there, one radius, two radii defines the distance between them. If we're in nonmetals, the right hand of the periodic table, they don't tend to form these like regular solid structures like this, but we can look at individual molecules. And the way that this is sort of done for nonmetals is the number that you would see quoted for an atomic radius. How big is this atom is sort of averaged together over many different structures. So it's not like, again, a precise number. But what they do is they would measure the distances in a variety of different molecules and a variety of different materials, and they would kind of report the average. So again, if you have like a Cl2 molecule, you could measure the distance between the two nuclei. There's different techniques for doing that. And what you would find is that this distance here is 199 picometers. I'm giving real numbers here. We don't have to memorize these, obviously. Pico is 10 to the minus 12th meter, so it's a very small number. And then the radius of chlorine atom would be that number divided by 2. Again, because we're considering two atoms bonded together, the distance between the two nuclei is 2 times the radius. So that gives you around 100 picometers. So that would be an approximate value for chlorine. Again, these numbers are approximate because they do vary a little bit. If you look at different molecules that have chlorine in them, you might not get that exact same number all the time. And then if you have a lot of the other ones, we do by difference. So if you have a carbon bonded to a chlorine, so if this is carbon and it's bonded to a chlorine, again, you have the two nuclei there. And so when two different atoms are bonded together, the distance between them is going to be the sum of the radii. So that would be 177 picometers, which is the radius for a chlorine atom plus the radius for carbon. We determined here that the radius for chlorine is about 100, so the radius for carbon would be around 77. So this is just more background information than anything, just to give you an idea of how these atomic radii are measured and what they kind of mean. And so again, over a wide range of molecules and materials, these distances have been measured, and then there's sort of some standard typical values that would then be reported for them. The important thing about what we're going to be doing today is talking about, based on the element's location on the periodic table, what would its radius be relative to something else? Not the exact numbers are super important, but more of, is this atom bigger or smaller? What happens if we move across the periodic table? Do they get bigger or smaller? Move down the column? All those sort of things that we're going to be talking about today are more important. So the key point about this, if we're talking about the general trend for atomic radius, is that if you go down a group, so down a group means down a column vertically. So we're talking about going in this direction. What you have to remember about how the periodic table is organized is that as you go down the group, the principal quantum number for the outermost electrons increases. So remember, each row of the periodic table represents a different principal quantum number, 1, 2, 3, 4, and so on. So as you go down, the principal quantum number increases. And so then, as we said, when the principal quantum number of an orbital increases, that tends to lead to electrons being further away from the nucleus on average. So that principal quantum number is related to the size of the orbital, how far away the electrons are from the nucleus typically. And so as we go down, the electrons get further away from the nucleus. And so that means the electron cloud is occupying more space. And so the radius increases as you go down the column of the periodic table. So the arrows that I'm going to draw today are going to be for increasing atomic radius. All right, so that's going to be, I think, the more straightforward one. Now, the one that's less, I guess, less intuitive, but hopefully will make sense to us as I explain it, is that if we move across a period, so that would be left to right or right to left, going horizontally in the periodic table. Now, a lot of people's first guess is that, well, if we're moving across the period, the atomic number is getting bigger, so that means the atom's getting bigger. But it doesn't quite work that way, because if you recall, as you move across a period, you're still putting electrons into the same valence orbitals. So that whole block of the periodic table that starts with boron there, boron, carbon, oxygen, nitrogen, you're putting all those electrons into 2p orbitals. So they're still in the same subshell in that whole block, but as you move across, you're adding more protons to the nucleus. And so it's those extra protons in the nucleus that are going to win out, and they're going to pull the electrons a little bit closer as you move left to right. So as we described it last time, that effective nuclear charge, Z effective as we abbreviate it, increases as you move left to right. So you're putting electrons into the same subshell as you move left to right in the same row of the periodic table, but you're adding more protons to the nucleus, so that pulls them in tighter. So when you increase your effective nuclear charge, the electrons get pulled closer, and the radius will go down as you move left to right. All right, so the direction then that would be increasing radius, which I'm drawing in red here, is right to left. So as you move right to left across a row of the periodic table, where can you find this? The book or the notes? I mean, I'm not sure what you're asking. So this is the February 4th notes. I hope I didn't post something wrong. Is anybody else having problems finding this? No? Okay, so the notes are labeled 02, 04, 25. So there's two sets of notes posted this week, so it'd be the first of those two. It's in the module section of Canvas. Yeah. So in the module section is where I keep all the notes, and they'll just be posted as a list, basically in order of date. All right, so the radius is going to increase as you go right to left. As you decrease the number of protons, the electrons get further away. So radius is fairly straightforward, and there's not really any exceptions to this trend that you need to be aware of. Weird things happen when you get down to the bottom parts of the periodic table. We're not going to talk about those in this class, but in general, you can just assume that this is a smooth trend. As you move top to bottom, the radius gets bigger. As you move right to left, the radius gets bigger, and there's not really any exceptions that you have to worry about. Now, the other periodic trends we're going to talk about today do have some exceptions you need to be aware of. It's a little bit annoying at times, but it's just the reality of the situation. So the next one we're going to talk about is ionization energy. We introduced this briefly when we talked about the Bohr model, but what it basically is the energy required to remove an electron from an atom. So we're going to talk about forming ions in more detail later today. And the amount of energy that it takes to remove one electron is called ionization energy. Now, it's specifically going to be defined for a gas phase atom. So what you have is an atom in the gas phase. The little G next to it means gas. And you're removing an electron completely. So you're going to form a positively charged ion, and you're going to release a free electron. And again, everything stays in the gas phase. And the change in energy for this process, which would be abbreviated as delta E, is referred to as the ionization energy. Now, what we also will see is that each atom is going to have multiple ionization energies associated. If it has more than one electron, there's going to be a certain amount of energy required to remove the first electron, and then a certain amount of energy required to remove the second electron. So we basically define ionization energies for each successive removal of an electron. So this one will be more specifically abbreviated as IE1. It's the first ionization energy, the amount of energy required to move the first electron to form the positive cation. And that's always going to be a positive number. So the electron is attracted to the nucleus, and so it's always going to you're always going to put energy in to rip that electron out and break that attraction. Okay. So the factors that influence ionization energy are it is sort of related to the radius. So as you go down a group vertically in a column of the periodic table, as we said, the principal quantum number increases, which means the radius increases. That's the trend we introduced last time. And that relates directly to ionization energy because as you go down a group, the attraction to the nucleus will decrease because the electrons are further and further away from the nucleus. Delta means change, so it's a change in energy. It's sort of the difference in energy between the ion and the atom, and that's how much energy it's put in to form that. So anytime you see delta in this class, which looks like a triangle, that means change, difference, final minus initial. That'll come in more detail later on in the course. So as you move down a column of the periodic table, the electrons get further and further away from the nucleus, so they have less attraction to the nucleus. It's easier to remove them. Your ionization energy decreases. So as you go down, the ionization energy decreases. And then as you go across a period left to right, same story. We said for this affects the radius as well. The effective nuclear charge increases and the size decreases. That's the trend we just introduced. So as the size of the atom gets smaller, as the electrons get closer, that means the attraction of the nucleus becomes stronger as you move left to right. It's effective nuclear charge. So it's basically the charge from the nucleus that the outermost electrons experience. It's going to be partially shielded by the inner electrons. So it's how much positive charge those outer electrons feel from the nucleus. All right, so that's going to be the factors that influence ionization energy. And so then what that leads to for the trend is, again, I'm going to draw it for increasing ionization energy, is bottom to top and left to right. And a very simple relationship, which is oversimplified in some sense, but as you go up a column or left to right, you're making the atoms smaller, so the electrons are held more tightly. They're closer to the nucleus. That makes it harder to remove them. And so that's why ionization energy increases as you go up and as you go left to right. In both cases, the atoms are getting smaller. Electrons are held tightly. Now, the thing with ionization energy and the next one we're going to do, electron affinity, there are several places where the trends break down. So it's not as smooth as the trend for radius. So this is the general trend for increased ionization energy, but there's going to be some places where it actually dips as you're moving, especially left to right. Up and down, there's really nothing to worry about in terms of exceptions. But as you move left to right across a row of the periodic table, there's going to be some places where, even though in general the ionization energy is increasing, there's going to be a couple of spots where it goes down a little bit and then starts going back up again. And so where that occurs, the most useful ones to remember are for boron and aluminum. That would be here and here. At those two places, you're going to have an abnormally low ionization energy. Actually, it's probably better. There's probably a better way to write this. I'm going to change how I do this a little bit. Um, so as you go basically from here to here, from group 2 to group 3, the group 2 elements have abnormally high ionization energies. And then for group 5, which would be the half-filled p subshells, that's going to be 1, 2, 3 here and here. I'll write that in red. All right, so group 2 is this column here, and then group 5, you're going to have also abnormally high ionization energies. So what that means, maybe the easy way to sort of understand this, is if we draw a plot here, this is all very qualitative, but if we have ionization energy on the y-axis and then group number here, 1, 2, 3, 4, 5, 6, 7, 8. So the columns of the periodic table are numbered, where the S and P blocks are going to be 1, 2, 3, 4, 5, 6, 7, 8. There's different ways of numbering the columns, but this is one of the more common ones, is to just number all the main group elements with just numbers 1 through 8. And those are the only ones where we're going to really consider periodic trends anyway. Things get weird in the transition metal. So you really just need to understand this for those 8 columns of the periodic table, the first 2 and the last 6. So if we go across those rows of the periodic table into those different groups here, what you'll find is that group 1 has a low ionization energy. And then, as we said, group 2 is abnormally high. And then it kind of comes back down with group 3, up with group 4, abnormally high for group 5, and then 6, and then 7. 8 is off the charts, but we don't really worry about group 8 because it's a noble gas, but it's way off the charts. But anyway, the general trend is that it increases, but there's going to be 2 spots, group 2 and group 5, where it kind of comes down off of that trend a little bit. And so as you go from group 2 to group 3, the ionization energy decreases. As you go from group 5 to group 6, it also decreases. It never skips more than 2 groups. So basically just the 2 that are next to each other are going to be the ones where you see that little break. So that's just something you have to kind of remember. As you're in group 2, the ionization energy is abnormally high, which means group 2 elements tend to have higher ionization energies than group 3, even though group 3 is to the right of group 2. And then similarly, group 5 to group 6, you're higher in group 5 than you are in group 6, even though you're moving left to right. So those are some trends you have to just practice and get used to, and you'll do problems that help you understand that better. Now, the other part of this, as we sort of said earlier, was the idea that every element is going to have successive ionization energy. So amount of energy is required to remove each electron if it's a multi-electron atom. So one electron at a time, how much energy is required for each of those steps. So what we would call the first ionization energy is the one that we just talked about, an atom in the gas phase losing one electron to form a positive charge. And then you would have your second ionization energy would be taking the cation where you've already lost one electron and taking off another electron. So it's going to be a different amount of energy that's required to do this. Now, for every element on the periodic table, as you go to higher and higher successive ionization energies, you go to the first ionization energy, your starting point, and then second, third, fourth, and so on. That number always gets bigger and bigger because you're trying to remove more electrons from something that's already positively charged. It gets harder and harder to do that. So for every element on the periodic table, the first ionization energy is the smallest, and then they just get bigger as you go across. So that's pretty easy to remember and hopefully easy to rationalize as well. So however many different electrons you have, each successive ionization is harder. It's harder to remove an electron from a cation than it is from a neutral atom. But what this table up here shows is that the specific way that those ionization energies increase can tell you something about that atom. So one of the concepts we introduced last time was the idea of valence electrons. Those are the outermost electrons, the ones that come after the inner noble gas core. And the number of valence electrons is characteristic of each group of the periodic table. So when we number the groups in this way, group 1 elements have 1 valence electron, group 2 elements have 2 valence electrons, 3, 4, 5, 6, 7, 8 valence electrons. The number of valence electrons is the group number when you number just the main groups, the S and P blocks. For transition metals, we said it's a little bit different. You have to include the S and the D electrons, but in general, the location on the periodic table tells you how many valence electrons there are. And that also then is going to relate to the trend for the ionization energy. So if we compare nitrogen and oxygen, so nitrogen has a valence electron configuration of, well, let's just write the whole thing out, but it's helium, and then the valence electrons are 2s2, 2p3. Oxygen would have a helium core, and then 2s2, 2p4. So they just differ by 1 electron. But the number of valence electrons for nitrogen is 5. The number of valence electrons for oxygen is 6. So if we compare the ionization energies for those two, a couple of things you'll notice. First of all, we said group 5 elements like nitrogen have abnormally high ionization energy. So even though oxygen is to the right of nitrogen, its ionization energy is a little bit lower. That's that blip in the trend we talked about last time. But also, more importantly, if we compare the successive ionizations of each of these elements, IE1 to IE7, we see that they do all increase. So they're getting bigger and bigger as we remove more and more electrons. But what we'll notice is that for nitrogen, which has 5 valence electrons, after the 5th ionization from 5 to 6, there's a huge jump. So it's going up gradually, 1.4, 2.8, 4.5, 7.4, 9.4, and then it jumps up to 53 after we remove all the valence electrons, 5 valence electrons. For oxygen, there's 6 valence electrons, so that huge jump doesn't come until after the 6th ionization. So the first 6 are kind of gradually increasing. You get up to 13, and then all of a sudden, boom, huge jump up to 71 for that 7th ionization after you've removed all the valence electrons. So what you'll see if you compare these trends is that there's going to be huge jumps in ionization energy after all the valence electrons are removed. So you can use charts like this, you can use data like this to predict how many valence electrons an atom would have and identify it in this way. And that's because it's very difficult to remove those core electrons. The core electrons are much closer to the nucleus, and those ones that are in the noble gas core. So once you've gotten rid of all the valence electrons, it becomes a lot more difficult to keep removing more electrons. So valence electrons are relatively easy to remove. The ionization energies will steadily increase as you keep removing more and more. But then once you finish removing the ionization, the valence electrons, the ionization energy is going to have a huge spike once you've gotten into those core electrons. So this one, nitrogen, the spike occurs from 5 to 6 because it has 5 valence electrons. So there's a huge jump there. Oxygen, the spike occurs from 6 to 7 because there's 6 valence electrons. After that 6 electron is removed, it becomes a lot more difficult to remove more. Okay, so that's something that ionization energies can tell you when we look at those that are beyond the first ionization energy. Now, one thing that I want to caution you about, though, I don't have time to go through like all the finer level details. This is something you'll have to work on as you practice on the homework assignments. But when we're using the periodic table to predict ionization energy, using the trends that I introduced and the fact that there's some abnormally high ones in group 2 and group 5, all that stuff, that only applies to the first ionization energy. So if you're using the periodic table, that only is going to allow you to predict ionization energy 1, the removal of that first electron. Anything beyond the first ionization energy, you have to think about how many valence electrons are left, how many valence electrons does the atom have. It comes more down to the electron configuration. So in general, after the first ionization energy, you would just consider the valence electron configuration and how many protons are in the nucleus. The periodic trends don't really work anymore after that. So I just want to make sure you're aware, and I'll maybe write that down here. This trend here, this general trend, is only for the first ionization energy. You don't want to use these types of arguments if you're asking to compare anything beyond the first ionization. Second ionization, third, whatever the case is, you first want to look at the electron configuration. How many electrons are you removing valence electrons? Are you removing core electrons? And then if they're the same from that standpoint, how many protons are in the nucleus? But only for the first ionization would this trend be the one that you would want to sort of look at and sort of use as your rationalization. All right, so you'll see that in the homework. There mistakes will be made. That's part of the learning process. So definitely try that out and see where the ones that don't make sense, and we'll address those as they come up afterwards. But I don't have time to go through all the possibilities today. All right. The last periodic trend we're going to talk about that's specifically for individual atoms. There's one more that's going to come that deals with atoms that are bonded to each other, but the one that specifically deals with just an individual atom is called electron affinity. It's not really the opposite of ionization, but it sort of is in some sense. So ionization energy refers to the amount of energy when you lose an electron. Electron affinity is the change in energy when it gains an electron, when it forms an anion. All right. So it's the energy change that accompanies the addition of one electron. So the process here is you're starting with an atom in the gas phase. So the starting point is the same as it is for ionization, a single gas phase atom. But this time you're adding an electron to it, not removing one. So you're forming a negatively charged ion, also in the gas phase. So the change in energy for this process, delta E, is referred to as the electron affinity. And again, we can have multiple electron affinities for the addition of multiple electrons. So this would be the first one, the addition of one electron. This delta E here, the difference also is that this is usually a negative number. With rare exceptions, which we'll point out, it's actually energetically favorable to add one more electron. And that's because you have protons in the nucleus, and they're happy to be attracted to one more electron. Remember, anytime there's an interaction between two oppositely charged particles, that's a stabilizing interaction. That would lead to a negative delta E when you're forming a new attractive interaction between the protons in the nucleus and an extra electron. So for almost every element on the periodic table, that's a negative number, which means it's happy to accept one more electron and become an anion. Not that um, not that elements and atoms have feelings, but you get the idea, I hope. So it forms a negative ion, and it's increasing the attraction to the nucleus, so it's a stabilizing type of process. So it's the factors that influence electron affinity are very similar to the factors that influence ionization energy, because again, it really boils down to how strong is that extra electron going to be attracted to the nucleus. And so the size of the atom influences that. So larger atoms tend to have smaller electron affinities. Now, when we say smaller, we mean less negative. So sometimes the sign conventions are a little bit confusing, but basically, as you said, electron affinity is almost always a negative number. So when we say something has a large electron affinity, that means it's a large negative number. When we say it's a small electron affinity, so we're talking about the magnitude of electron affinity when we're comparing things across the periodic table and saying this one is smaller, this one's larger. It refers to the magnitude of that number. So larger atoms tend to have smaller electron affinities, again, because the electrons that you're putting in are going to be further away from the nucleus. They're going to have a smaller attraction to the nucleus. Same argument we've been making in other contexts today. And then as you move left to right and you increase that effective nuclear charge, again, there's exceptions to this, but in general, as you move left to right, your higher effective nuclear charge leads to a larger, or what you would say is a more negative electron affinity. So when we say electron affinity is larger, we mean that it's a larger negative number. We're comparing magnitudes here. All right, so if we look at the general trend for electron affinity, the general trend is the same as ionization energy. Increases bottom to top, increases left to right. So in general, your ionization energy gets larger in those directions. As does your electron affinity. So that's going to be the general trend. But again, there's some breaks in the trend, and they come really in the same spots of the periodic table. So the nice thing is all these exceptions we're talking about for ionization energy and for electron affinity, those occur in the same groups of the periodic table. They occur in opposite directions. So we said that group 2 here has an abnormally high ionization energy. It has an abnormally low electron affinity. I'll write it with a number, but sometimes they're done with Roman numerals as well. But group 2 has abnormally low electron affinity. And then same with group 5 here in the middle of the P block, abnormally low electron affinity. The reasons for this are kind of complicated. I don't want to try to oversimplify it. So the best thing is just to try to remember that. But basically, again, if you were to draw the trend as you go across the main groups of the periodic table, 1 through 8, the other thing to realize, it's not even going to come up in any of the problems, so it shouldn't cause any confusion for you in a real setting. But group 8, which is the noble gas column, has basically 0 electron affinity. Those noble gas configurations where you have S2P6, those are the most stable electron configurations. So they don't want to lose electrons. They have really high ionization energy. They also don't want to get any more. So they basically have 0 electron affinity. There's no desire for them to pick up an extra electron. But that's not going to really come into play. We're mostly going to just compare the other 7 groups, 1 through 7. And again, just like ionization energy, the general increase is going to be left to right, but there's going to be breaks in the trend at group 1 and group 2. So group 1 has a pretty low electron affinity, but group 2 is even lower if it lies off of that trend. Then you kind of step up with group 3 and group 4. Group 5, as we said, is abnormally low, kind of dips way down, and then group 5 and group 6 continue upwards. So the important thing to remember is that group 1 and group 2 tend to have low electron affinity. It actually decreases a little bit going from 1 to 2. And then as you go to the right of the periodic table into the nonmetals, the electron affinities tend to get higher and higher, but there is a dip again at group 5. So group 2 and group 5 are always the 2 places where those breaks in the trend come up. And that's because, again, I don't want to get into too much of the details, but in group 2, you have an S2 valence configuration. Group 5 has an S2P3. Both of those are abnormally stable electron configurations. If you have a filled s orbital, you don't want to add or subtract more electrons from that as easily. And if you have a half-filled p orbital, same story. It doesn't, and then it gets even more extreme in group 8, as we talked about a little bit too. So those are the ones where they're happy where they are. They don't want to lose electrons, they don't want to gain electrons, and so that's where you have those breaks in the trend that we talked about. So same spots, just opposite direction. Abnormally low for electron affinity. All right. So any questions on those topics? I believe that takes us to the end of chapter 2. Yeah. One more slide. Okay. So the any other questions? We're not missing anybody. Okay. Uh, so we're gonna jump into chapter 3 now. And so chapter 3 is we're now moving on past individual atoms. So everything we talked about in chapter 2 was about a single atom. Its electron configuration. We just finished talking about some of its key properties, orbitals, all that stuff that deals with a single atom. Now in chapter 3, the topic is going to be how do two or more atoms come together to form bonds? And the first type that we're going to talk about are what are called ionic bonds. And what you're really doing here is you're taking atoms, and one atom is going to lose one or more electrons to make a cation, a positive charge. Another atom is going to gain one or more electrons to make a negatively charged ion, and those two are going to be attracted to each other, just like anytime you have a positive and negative particle, they're going to attract one another. So that's what's called an ionic bond. You're making actual ions where one thing is losing electrons and another is gaining them. And the nice thing is, based on the location in the periodic table, you can pretty easily predict which type of ions will be formed. Do these atoms tend to lose electrons and form positive ions? Do these atoms tend to gain and form negative ions? And how many of those electrons will they gain or lose? That all comes again from the location in the periodic table. So group 1A, which is the first column of the periodic table, those have S1 valence configurations. And so generally when atoms when atoms end up forming ions, when they lose electrons to form a cation or gain electrons to form an anion, they will lose or gain the number of electrons that's required to get to the nearest noble gas configuration. We said those noble gas configurations are very stable, so they want to get to that. So if you're in the first column of the periodic table, which excluding hydrogen, which is a nonmetal, but all the metals in that column, lithium, sodium, potassium, rubidium, cesium, and francium, those can just lose one electron and get back to the next noble gas that comes before them. So all of these group 1A cations, the ones that are in the first column of the periodic table, they all tend to form +1 cations. So that would be pretty much all of them. Lithium, sodium, potassium, rubidium, and cesium. I guess francium would too, but francium is radioactive, so we don't play with it too much. But that's the general trend. That whole first column periodic table, you would predict if they're going to form ionic compounds, they would lose one electron, form a +1 cation. The pattern continues for group 2. Group 2 has an S2 valence configuration, so by losing 2 electrons, they can get back to the next noble gas that comes before them. So those cations in group 2 tend to be +2, so beryllium, magnesium, calcium, strontium, and barium all form 2+ cations, that whole column. Now, as we go to the right side of the periodic table, the P block, the middle parts are, again, for predicting ions, a little bit more confusing. So we won't do as much with those. We'll point out some things about those, but not a whole lot. But the other place where you can make pretty easy predictions is on the very right of the periodic table, group 5, group 6, and group 7. So group 5 starts with nitrogen, and it has the S2P3 valence configuration. Now here, the choice is, do I lose 5 electrons to become a +5 cation, or do I gain 3 electrons to get to the next noble gas that comes afterwards? It turns out when you're on the right hand of the periodic table, because they have higher electron affinities, and because it's fewer electrons to get to the noble gas by adding electrons, they tend to form anions, okay? So in group 5A, you would form -3 anions. You would add 3 electrons to this to get to the S2P6 valence configuration, which is the noble gas stable configuration. Not all of the elements in this column behave that way, because as you go down group 5, you cross over from nonmetals into metals. So nitrogen and phosphorus are nonmetals, but then as you go down to arsenic, it's a metalloid, and then Sb, which is antimony, and Bi, which is bismuth, kind of are more like metals. But for the first two, nitrogen and phosphorus, they tend to form -3 anions. So N3-, P3- are predicted to be the stable anions for those two elements. It gets trickier as you go down, so those are the only two that you should easily be able to predict. Group 6A has S2P4 configuration. So by gaining 2 electrons, they can get to the stable S2P6 configuration. So they form -2 anions. oxygen, sulfur, and selenium all follow that pattern. Again, as you get too far down that column into tellurium and polonium, they behave more like metals or metalloids, so they don't really follow the same pattern necessarily. And then for group 7A, you're just one electron away from the noble gas configuration, so you can gain a single electron, make a -1 anion, and all the halogens behave in this way. Fluoride, chloride, bromide, iodide all form -1 anions. One other one that you should definitely remember that's not in this chart here is aluminum will always form 3+ cations. So aluminum is right here in the periodic table, number 13. I'll go back to it in a second. So aluminum is right here, number 13. So it tends to, it's in the P block of the periodic table, but it's a metal. And so it's going to lose 3 electrons, 1, 2, 3, to get back to the neon configuration. So aluminum forms +3 cations. That's another one that's important to remember. So you should remember aluminum 3+. The rest of them, based on location in the periodic table, it's fairly obvious. So you always predict that that's the type of cations and anions that will be formed by each of these elements, depending on which column of the periodic table they're in. Very easy for the main groups. We won't talk as much about transition metals. They're more complicated. They usually have more than one possible ion they can form. But for these main group elements, it's very straightforward. So the first thing we're going to discuss a little bit are the electron configurations of the ions. So if they lose or gain electrons, where do those electrons go? What's the new configuration for that ion? And generally, it's pretty easy to do because for anions, you just keep adding electrons into the partially filled subshell, typically until you fill it up. So it's just going to fill that last, usually p whatever configuration. That's what we do for anions. You just add electrons to the partially filled subshell. So just like we do for regular electron configurations, we just keep adding more electrons to the lowest energy available subshell. In this case, when you're forming anions, you're typically going to have a partially filled p subshell, and you'll just keep adding electrons to it. Always to fill it up is what typically happens. So if we have oxygen here, which has the configuration of 1s2, 2s2, 2p4, that you should be able to predict by now pretty easily. It's in the fourth column of the p block, so it ends with 2p4. If we add 2 electrons to that to make the oxide anion, where do those extra 2 electrons go? Well, they're going to just keep going into the 2p subshell because there's room for 2 more electrons. Remember, the 2p subshell has 6 columns in the periodic table. There's 3p electrons, 2 electrons each, so you can put up to 6 electrons in there before it's completely filled. So those extra 2 electrons are going to just fill those 2 extra spots. So it's going to be 1s2, 2s2, 2p6, which again could be abbreviated as the neon configuration. The formation of these ions in the main group, the S and P blocks, tends to get you to the nearest noble gas configuration. So that's exactly what happens here. O2 minus has the same configuration as neon. Those last 2 electrons go into the 2p subshell. When you're forming cations, again, we're going to mainly just talk about the main group cations in the first 2 columns of the periodic table. The rule is basically the last electrons that go in are the first ones that come out. So you just remove the valence electrons to do that. So when we form cations from the S block elements, the first 2 columns of the periodic table, you're going to remove the outermost S electron or electrons, 1 electron if it's group 1, 2 electrons if it's group 2. Again, those are the ones that have the highest principal quantum number. So if we start with sodium, which is Na, we did the configuration for sodium last week. It was 1s2, 2s2, 2p6, and then 3s1. We will predict from its location on the periodic table that it wants to form a +1 cation. And so it's going to remove 1 electron to form the sodium plus cation. And so the configuration for that would be we remove the outermost s electron, the one that has the highest principal quantum number, the last one that we put in, which is this 3s electron here. So that's the one that goes away, and the new configuration will just be 1s2, 2s2, 2p6, which again is the neon configuration. So both of these stable ions, the O2 minus anion and the sodium plus cation, both have the neon configuration. So for cations, you remove those last electrons that you would put into the neutral atom. The last one's in or the first one's out. So those are the types of configurations you should easily be able to predict. Let's also talk a little bit then about the sizes of ions. So we just introduced earlier today the idea of atomic radius, how big an atom is, relatively speaking. And so if you add or remove electrons from an atom, does it get bigger or smaller? How do we compare those when there's charges involved? So typically speaking, if you have cations, if you remove electrons, they're always going to be smaller than the parent atom. And hopefully that's fairly obvious because we're removing the outermost electrons. We're removing the electrons that are furthest away from the nucleus, so the ones that are left are, on average, closer to the nucleus. That means the atom gets smaller. Okay, so whenever you remove electrons, you're taking away the ones that are furthest away from the nucleus. That makes the atom shrink. It's usually a pretty dramatic effect, too, if you look at the real numbers for this. The other thing that can occur is that for some elements, you can have multiple different cations observed. So if you have the same element with different amounts of positive charge, the higher the positive charge, the smaller the cation. So the more electrons you remove, it's going to get smaller and smaller, is another way to think about that. So for example, the element lead, which has the symbol Pb, this is not one that we would be able to easily predict from what we're covering in this class, but lead is a metal that can form both +2 and +4 cations. It's S2P2, so basically it can lose either the 2p electrons to form a +2 cation, or it can lose all 4 of those valence electrons to form +4. You don't need to be able to predict that necessarily, but if you have both of those cations, you would predict that lead 2+ is smaller than lead, because every time you remove electrons, it gets smaller. And then if you go all the way to lead 4+, it gets even smaller than that. So they get smaller and smaller the more electrons you remove. Okay. And then opposite is true for anions. So anions tend to be, always are anyway, larger than the parent atom, the neutral atom. I don't know which word you're having trouble with. Removing outer electrons. All right, so then the anions are going to be larger. Really opposite story here for anions. Larger than the parent atom. And this one is maybe not as obvious. Why? Because we're adding electrons to the same subshell. We just said that, okay, if we're making an oxide anion, O2-, we're still putting more electrons into the 2p subshell. And so it's still in the same subshell. It really should be similar distance from the nucleus, right? But it still gets bigger because as you add electrons to the outer shell, even though they're in the same subshell, you increase the electron-electron repulsion. E- is an electron, yeah. It's an abbreviation for electron. And so when you have like oxygen, the one we just talked about, as a neutral atom, it's 2s2, 2p4. So in the 2p subshell, you have 4 electrons. And then you try to add 2 more in there. They're still in this same 2p subshell, but now you have 6 instead of 4. So there's more electron-electron repulsions, and they tend to spread out a little bit more to accommodate that. And so that makes them bigger. So however you want to rationalize that to yourself, basically anytime you add electrons, you make the atom bigger. Now, a special category that we're going to talk about at times are called isoelectronic atoms and ions. These are going to be atoms or ions that have the same number of electrons. So the radius for these is those that are cations are going to be smallest, neutral going to be biggest, in the middle, and then anions are going to be bigger than that. Let me write is negative. That's more grammatically correct here. All right, so as an example, all of these ions and atoms have the same number of electrons. Calcium 2+, K+ potassium, argon, Cl minus, and S2 minus. All of these have the argon configuration. They all have 36 electrons. Or sorry, 18. So they all have 18 electrons, or all the argon configuration. But the ones that are positively charged are going to be the smallest. They have the most protons, so they pull the electrons closer. The ones that are negatively charged are going to be the biggest. So all of these have the same configuration, but this is the order of their sizes because the ones that are positively charged have more protons, so they pull those same electrons closer. And so again, if you're comparing the sizes of ions, you do need to think about the electron configuration, not just location on the periodic table. That only works for neutral atoms. For ions, you want to think about the electron configuration. And if all the ions have the same configuration, like this set here, it really is going to just go in this order. The ones that are the most positively charged are the smallest. The ones that are the most negatively charged are the biggest. All right. Now, the more important thing to talk about moving forward are going to be predicting the formulas of ionic compounds. So when an ionic bond or an ionic compound forms that involves ionic bonds, you're going to have some cations, atoms that have lost electron, and some anions, electrons, atoms that have gained electrons, and they're going to combine in some ratio. So basically what has to happen is that the cations and the anions are combined in a ratio that balances the charges. That's really what it boils down to. So there can be no net positive or negative charge in an ionic compound. So as a very simple example, and one that you're familiar with from your everyday life, when sodium and chlorine combine to form sodium chloride, which is table salt, sodium is in the first column of the periodic table. So as we talked about, it forms a +1 cation. Chlorine Cl, number 17 over there, is in the second to last column. And so it's going to gain one electron to form a -1 anion to get the noble gas configuration. So those two, when they combine, sodium has a +1 charge, chlorine has a -1 charge, and so they're going to combine together in a 1-to-1 ratio to make sodium chloride. Because one positive and one negative charge balance each other out. So that's the simplest case. Now, when you write the subscripts for an ionic compound, which is going to tell you the relative numbers of each atom or ion that you have, you always want to use the smallest whole numbers possible, the smallest ratio. So never fractions, but also you don't want to use subscripts that are reducible either. So if the subscripts are 1, you don't write them explicitly. So it wouldn't be written as Na1CO1. It would just be written as NaCl, as we said. But it would be incorrect to write it as Na2Cl2 or Na3Cl3, for example. Those still balance the charges correctly. You have the same number of positive and negative charges, but they're not the smallest ratio. You want to reduce that down all the way to 1-to-1 in this case. So you want to write them as the smallest ratio. So some examples of how would we predict the formula of ionic compounds? There's actually a very simple and almost brainless way to do this, which is that if you know the charges of the cations and the anions, here I'm just giving you, okay, we're making an ionic compound with calcium 2 plus and O2 minus. Even if I didn't tell you that, you could use the periodic table to predict that calcium forms 2 plus cations, oxygen forms 2 minus anions. So you know the charges of the individual ions that are involved. And what you can do in this case is you write out the charges, and then the charge on one ion becomes the subscript on the other. So this 2 here becomes the subscript on oxygen. This 2 here becomes the subscript on calcium. So you could write it as Ca2O2, but then we need to reduce it because 2 to 2 reduces down to 1-to-1. So this would also be a 1-to-1 ionic compound, CaO, 1 calcium, 1 oxygen. In this case, the charges are +2 and -2, but they still balance out if we just have 1 cation and 1 anion. So there's more charge involved, but they're still balanced out with the 1-to-1 ratio. If we do Ca2 plus and N3 minus, we need to figure out what is the ratio of those two that would balance the charges. And here it's a little bit more tricky because the positive and negative charges aren't the same as each other. So if we just had one of each, we wouldn't cancel out all the charge. You'd still have extra negative charge. But again, the simple way to do this would be to take the charge from one ion and make it the subscript on the other, and vice versa. So that comes out to this 3 becomes a subscript on calcium. This 2 becomes a subscript on nitrogen, so Ca3N2. 3 to 2 is the smallest whole number ratio. You can't reduce that down any further. We don't want fractions in our formulas. So Ca3N2 would be correct. So for calcium, you would have 3 ions that are +2 each, which is +6 for positive charge. For nitrogen, there's 2 anions that are each -3 in charge. So that's -6. So +6 and -6 do cancel each other out, but you need different numbers of those to get the charges to balance. All right, so that's one thing we will expect you to do starting in this part of the course, but really continuing on through a lot of things that are come up in the future is predicting the formulas of ionic compounds. And there'll be more details on that towards the end of this chapter as well. So that's just a brief primer on that. The last thing we're going to talk about today are covalent bonds. So a covalent bond is a situation where 2 atoms share their electrons. So they don't give them up to form positive cations, or they don't gain more electrons to form anions, but they actually bring 2 atoms together and they share their outermost electrons with each other. 2 electrons being shared for each bond that's formed. A lot more details about this to come later on, but that's sort of the simple way to think about it right now. 2 atoms bonded together by sharing their outer electrons with each other. So there's a few properties of covalent bonds that we want to be aware of. So one of them is called bond energy. This can have different names. Sometimes it's called bond strength, or a more formal term is bond association energy. So all these mean the same thing. Just want to make sure you're aware of the different terminologies we have. So bond strength, bond energy, bond association energy, and both bond association energy all mean the same thing. And basically, this is the energy required to break a bond. Now, the slightly confusing thing at this point, which you don't need to worry about too much, but these bond energies are always defined as the amount of energy it takes to break 1 mole of that bond. So if we have the simplest molecule H2 with 2 hydrogens bonded to each other, it's not the amount of energy required to break the bond in 1 molecule of hydrogen. It's the amount required to break the bonds in 1 mole, which is a whole huge collection of hydrogen molecules. We're going to define that more detail later on, but it's for an amount of substance that we'll cover later on. But that's how bond association energies are defined. But it's the amount of energy required to break the bond. It's just defined as for a whole mole of that substance, not for a single one. Still defined in the gas phase like the other properties. So it would be if you have 2 atoms bonded together, A and B, in the gas phase, it's the amount of energy required to separate them into the individual atoms, A plus B, to completely break them apart from each other. So the delta E for this process, also referred to as the bond energy for that bond AB, always a positive number. The 2 atoms are stuck together by that bond, by that sharing of electrons. You have to put energy in to rip them apart. So it's always a positive number, and that's the amount of energy that's required. So that's the amount of energy required. And from this diagram here, what you can basically see is, I didn't want to cover this in too much detail, but this type of diagram describes the potential energy of 2 atoms as you bring them closer together and form a bond. So if they're far apart, there's no energy of interaction. As you bring them closer together, the electrons from one atom start attracting to the nucleus of the other, and they start coming together and forming a bond. So you get to this minimum here. And then as you bring them too close together, electron or electron repulsion starts dominating and the energy goes back up. So you have this sort of sweet spot here. And so this bottom part of this potential energy well, as it's called, the y-axis gives you the bond energy, or the negative of it, I suppose. So that's how much energy those 2 atoms are attracted to each other in their stable geometry, and so you need that much energy to break them back apart. So that's the negative of the bond energy there. I don't know if these diagrams are going to come up. I just want to introduce it once quickly. The other key property of bonds that we're going to talk about is the bond length, and this is going to be the distance between the nuclei in 2 atoms that are bonded to each other. So if we have A and B bonded together, let's say A is much smaller than B, for example. These are their electron clouds that are shared. These are the nuclei. That distance there is the bond distance. Okay, the distance between the nuclei. It's related to atomic radius that we talked about before. And then the key, and then here on this diagram here, this would be the bond distance. That distance between the two nuclei where you get to that minimum energy value. So the bond distance in this case would be about 125 picometers in this random example. A key point we're going to bring up is that bond distance is inversely related to bond energy. So if we start comparing one bond to another, what we will find is that bonds that are longer tend to be weaker, bonds that are shorter tend to be stronger. Sorry, I'm losing my voice here. All right, so that's going to be something we're going to want to keep in mind. So the shorter the bond is, the closer the two nuclei are together, the stronger they're going to be holding on to those shared electrons. If the bond is longer, the atoms are farther apart. The electrons that are being shared are further apart from the nucleus that's holding on to them, and so it gets weaker. So that's the key relationship between those two properties. Another property that we have to consider that's going to then factor into those two as well is called the bond order. The bond order is the number of shared bonding pairs. So every time two electrons are shared, that's one bond. But sometimes atoms can share more than two electrons, so they can form more than one bond that's covalent. So if they share two electrons, that's one bond. If they share four electrons, that's two bonds. And that number of shared pairs is referred to as the bond order. So when we say that something has a single bond, that means the bond order is 1. And that means there's one shared electron pair. And each bond is a pair of shared electrons. So the simplest molecule that we have, H2, has a single bond between the two atoms. So we write that either as just a single line, a line indicating one bond or one pair of electrons that's shared, or you'll sometimes see these electron dot diagrams where we actually draw out the electrons individually. But that, again, a single bond would have two electrons shared in between the two atoms. Okay, that's a bond order of 1. A double bond would be a bond order of 2. And that means you have two bonding pairs. We will learn later on how to predict what the bond order should be in simple molecules. But an example of a double bond would be when you make O2, two oxygens bond to each other, they make a double bond. So that's going to be most typically indicated as two lines in between the atoms, where again, each line is one bond, one pair of shared electrons, or sometimes you'll see, again, electrons written out individually like that. Not as common, not as user-friendly, in my opinion, but that's another way of indicating that. The highest that will go in this class, because we're only going to be talking about bonding in the main group metals, the covalent bonds involving primarily just the P block over there on the right side of the periodic table, the highest you can get to is a bond order of 3. That's the maximum. If you go to the transition metals, the part of the periodic table that I'm most interested in, you can get quadruple bonds or even quintuple bonds. But for our purposes, triple bond is the highest. So bond order of 3 is the maximum for us in the parts of the periodic table that we're going to concern ourselves with, and that would have 3 bonding pairs. So nitrogen forms triple bonds with itself when you make N2, the most abundant gas in our atmosphere, which again, most commonly written as 3 lines, or 3 pairs of dots shared between 2 atoms. For each pair of dots is 1 bond. All right, and then the key thing about bond order is that, and this is a pretty significant effect too, so it's one of the most important things to think about. If we have a higher bond order, we're going to have shorter bonds. The more electrons that are shared are going to pull the nuclei closer together, and that leads to it being a stronger bond. So that's one of the most important factors that's going to determine how short and how strong the bond is. If you're comparing a single bond to a double bond to a triple bond, you would expect the triple bond to be the shortest bond and also the strongest bond. It's a very big effect every time you increase the bond order. All right, so if we're talking about then how to compare trends in bond lengths, let's look again at just a couple examples of how to do this. So a common problem you might see on upcoming homework assignments that deal with this chapter are, what is the relative bond lengths of these three? So I'm going to give you here three: CF, C double bond O, C triple bond N. Which one's the longest? Which one's the shortest? What order do they come in? So when you're comparing bonds, the first thing you want to look at is the bond order. If the bond orders are different, use that as your primary determining factor. Maybe the one exception to that is if you have two hydrogens bonded to each other, that's the shortest bond you can have because a hydrogen is tiny. But in general, if you're comparing atoms from the same part of the periodic table, so CF, CO, CN, all of those are in the 2p block of the periodic table, similar part of the periodic table. The first thing you want to look at is the bond order. And again, higher bond order means shorter bond. So even though there's different elements involved for each of these, carbon is common between them, but carbon bonded to fluorine, oxygen, nitrogen. If the bond orders are all different, use that as the factor that you would rank them by. So for the bond lengths of these three, the single bond should be the longest, and then the double bond, and then the triple bond. So if bond orders are different, use that as your primary determining factor. Now, there's also going to be a lot of problems where the bond orders that you're comparing are all the same. So this example down here, we're comparing CF, CCl, and SiCl. They all have single bonds, so we can't use bond order to help us decide which one's longer, which one's shorter. So the second thing that's going to be involved is the size of the atoms. So we learned how to predict relative atomic radius earlier today. So you might not be an expert at it, but it's something we've already covered. And then the bigger atoms tend to form longer bonds. And hopefully that makes sense. If the atom's electrons are further away from the nucleus, when it comes together with another atom to form a bond, they can't get as close to each other because they both have bigger size. So if we compare these three here, CCF, CCl, and SiCl, you want to sort of compare them two at a time and look at things that are in common between them. So if we compare the first two, CF and CCl, they both have carbon, and one of them carbon is bonded to fluorine, and the other one carbon is bonded to chlorine. So if we compare those two, let's go to the periodic table. We would find that fluorine is here, number 9. Chlorine is right below it, number 17. So as we move down from fluorine to chlorine, we expect the atoms to get bigger. So chlorine is bigger than fluorine. That means we would expect the bond between carbon and chlorine to be longer than the bond between carbon and fluorine. So those two, we would expect this one to be the bigger one because chlorine is bigger than fluorine. So carbon and chlorine can't get as close together when they form a bond. That bond will be longer. And then the last one we have to compare is silicon chlorine with one of these two as well. So again, it's the easiest comparisons are ones where one of the atoms is the same. So this one here, the CCl bond and the SiCl bond both have chlorine in them. So whichever one is larger, carbon or silicon, is going to give us the longer bond length with chlorine. So that also ends up being a pretty straightforward comparison because carbon is there, silicon is there. I have to flip back and forth. So it'll get back to it. So then those two again, silicon is below carbon, so it's going to have a larger radius. That means its bond with chlorine should be longer than the bond with carbon. And so again, for these two here, silicon chlorine bond would be longer than the carbon chlorine bond. So that's how you go about doing comparisons when the bond radius is, when all the bond orders are the same. You look at the atomic radii. The bigger the radii of the two atoms that are combining, the longer the bond is going to be. So that's another factor you'll have to come into play. All right, the last topic we're going to talk about today for covalent bonds is what's called electronegativity. So this is going to be the last periodic trend we have. But the difference is, unlike the ones that we covered earlier today, those are properties of a single atom by itself. Electronegativity is the property of an atom when it's bonded to another atom. And what it basically boils down to is it's the relative ability of a bonded atom, so an atom is bonded to another one, to attract the shared electrons. So the whole idea here with electronegativity, and then the related concept that we're going to finish with, which is called bond polarity, is that when two atoms share electrons in a bond, they don't necessarily share them equally with each other. Okay. So as an analogy that might work for some of you, fun fact, I have an identical twin brother. So we shared a room growing up, same size, roughly, same strength, all that. So we shared our space very equally because of that. He couldn't, bully me to take more space. I couldn't do the same to him. But if it was a much older brother and a much younger brother sharing a room, you might expect that the older brother would have more of the space. The space would be shared, but not equally. And same thing is true when atoms form a bond, even though they're sharing two electrons to make that bond, they're not necessarily sharing them equally. More of the electron density could be skewed towards one atom versus the other. So that would be what's called a polar bond. We're going to get into that, but that's determined by the electronegativity of the atom. The more electronegative the atom is, the more it pulls the electrons towards itself, the more it hogs those shared electrons, okay? So the scale for electronegativity, it's a pretty compressed scale. It's not a very precise or accurate thing, but it is a relative scale that we'll be a little bit familiar with. And it was derived, the one that we commonly use today was derived by Linus Pauling, a very famous chemist who's pictured above. Spent most of his career at Caltech in Southern California. And basically what it boils down to is that it's a scale that more or less goes from about 1 to 4 for most of the periodic tables. It's not a very big, wide scale. The highest electronegativity on the periodic table is fluorine. We don't need to necessarily memorize the numbers, although it's helpful to have a few benchmarks in mind. So the electronegativity for fluorine is 4.0. That's the largest electronegativity that you can have. And then the smallest electronegativity values are in the opposite corner. So fluorine's in the top right. You go down to the bottom left, cesium and francium. Those two down there have the lowest electronegativity, which on this scale is 0.7. Just, we don't need periods there. That's just En. It's fine. It's only one word. All right, so En for electronegativity. So that's kind of the scale that we're talking about. So where does this scale come from? The way that it was derived is if you have a bond between two different atoms, A and B, if the Linus Pauling is the name of the person, yeah. So if you have two atoms bonded together, A and B, the expected bond energy would be, if the electrons were shared perfectly equally, would be the average of the two. So if there was perfect sharing of the two electrons, if you knew the bond energy for A with itself and you knew the bond energy for B with itself, the average of those two should be the bond energy of A and B. But in most cases, they're going to be different from each other, and that's because of differences in electronegativity that draw the electrons closer to each other or further away from one atom or the other. And so the way that this scale was developed, we're not going to go through all the details, was that he averaged together experimental bond energy values for a bunch of different combinations of atoms, found out where they deviated from these predictions, and then allowed him to develop a scale using that. Okay, so the electronegativity trend is essentially the same as the other ones, and there's not really any exceptions we have to worry about. It increases bottom to top and left to right. So increasing electronegativity in that direction. Again, left to right across a period, it goes up, and then down a group, it goes down. So it's going to increase in the opposite direction. And it's the same trend as electron affinity, which it's kind of related to. The nice thing is there's no exceptions we have to worry about. It's a smoother trend, and at least for our purposes, we don't have to worry about any exceptions. There might be some here and there, but nothing that's going to concern us. It's the same trend as electron affinity, which it is closely related to. And when I say it's closely related, we have to understand it's not exactly the same thing. Electron affinity is the attraction that an atom has for an extra electron to itself, and just when it's all by itself to form an anion. For electronegativity, we're talking about when the atom is bonded to something else, how strongly it pulls the electrons towards itself. So it's slightly different, but it is related. So that's why the trends all kind of trend on top of each other. So what this leads us to is a concept called bond polarity. So this is the idea that sometimes when electrons are shared, they're not shared equally. So when the atoms have different electronegativity values, the sharing of the electrons won't be equal to each other. So when these atoms form a bond, however many bonding pairs you have, one or more if it's a single bond or a multiple bond, these bonding pairs are not going to be shared equally. They're going to be shared unequally. All right, and again, that's what electronegativity determines. If there are two different electronegativity values, then they're not going to share the electrons equally. And the one that has the higher electronegativity is the one that's going to pull the electrons closer to it, have more electron density around it. So how we indicate this is in two different ways. One that you might see is with an arrow. So if we have hydrogen and fluorine bonded to each other, the electronegativity of hydrogen is 2.1, fluorine is 4.0. It is helpful to remember about where hydrogen is. It's kind of in the middle of the scale because it is in a weird spot in the periodic table relative to where it should be. But hydrogen is about 2, which is roughly the same as carbon. So it kind of fits right into the middle of that P block there in terms of electronegativity scale. But fluorine is more electronegative, so that means it's going to hog the electron density. So one way we indicate this is with a vector, an arrow that points towards the more electronegative atom. Arrow is R, is/R. Thank you. So that's one way to indicate polar bonds. You have an arrow pointing towards the more electronegative atom. Probably the more common way in chemistry is in this way here. So we have the two atoms bonded to each other, and you put a lowercase delta with a positive and a lowercase delta with a minus. So in this case, what you have is you indicate a partial negative charge. Delta means partial in this case. The lowercase delta here means you have a partial negative charge on the more electronegative atom. All right. So that would indicate again that fluorine is hogging electron density, so it's not a full negative charge. It's not completely stealing the electrons from hydrogen. They're still shared, but it's pulling them towards itself. I'll fill out the last slide before I post the notes, but the whole idea of this last slide is that there really is a continuum between perfectly covalent, where the electrons are shared exactly equally. That's when you have the same atom bonded to itself or the same electronegativity. And then ionic bonds is the other extreme where the electrons are transferred. And basically every polar bond is sort of in between those two extremes. So, read that part of the notes. I won't be able to cover it since I'm missing Thursday, but it'll be there, and we'll come back next week with other topics related to this last chapter before the exam.